Hi, my name is Joseph Tyndall, and this is the video abstract for our paper titled Quantum Synchronization Enabled by Dynamical Symmetries and Dissipation, which I wrote with my collaborators Carlos, Berislav and Dieter here at the University of Oxford. Synchronization is a fascinating phenomena where groups of individual bodies adjust their natural rhythms upon interacting with each other. It can be observed all around us, from the flights of birds to the congestion of traffic. Synchronization is a fundamental phenomenon which drives many of our everyday experiences.
In our paper, we focus on synchronization in quantum systems. In the quantum world, the energy and length scales are much smaller than in the world around us. The focus is on individual atoms and electrons whose behavior can be quite different to what we're used to. Understanding how synchronization can arise in these systems and what impact quantum effects such as entanglement can have on this phenomenon is a large field of research within the quantum community.
In this work, we lay out conditions which, when satisfied, guarantee that perfect synchronization can occur in a generic quantum system, independent of any specific microscopic details. We then identify several physical features whose interplay can ensure these conditions are satisfied and the system reaches a synchronized state in the long time limit. The observed synchronization is reminiscent of that of classical synchronization, with the individual constituents undergoing locked limit cycles. The underlying mechanism, however, is based on entanglement and superposition, which are intrinsically quantum properties.
Previously, we identified how the existence of certain symmetries, known as strong dynamical symmetries, can guarantee that instead of decaying to a generic stationary state, a quantum system coupled to an external environment reaches a non-equilibrium state, undergoing coherent oscillations for an indefinite period of time. In this work, we show that if all of these symmetries are completely translationally symmetric, then not only do the constituents of the quantum system undergo long time limit cycles, but they will synchronize perfectly together. We prove that this synchronization process is robust to perturbations in the frequencies of these constituents as well. It is known from prior research that the interplay between interactions and local dephasing in a quantum system can drive it into a state that is built from completely translationally invariant operators. There is no longer any geometry in the system, and all long-range correlations are invariant with distance. Hence, a combination of local dissipation and interactions in a quantum system on top of the existence of a strong dynamical symmetry effectively forms a recipe for ensuring synchronization can happen in a generic quantum system. One of our examples where this synchronization can be observed is that of a chain of Q-tricks. These are free-level spins which interact with each other and are coupled locally in a spin-agnostic manner to an environment. This system has all of the ingredients required for our synchronization recipe. Our simulations show how these Q-tricks synchronize perfectly when initialized in a random state. If we remove one of our ingredients, say interactions, we observe the expected limit cycles of these Q-tricks, but there is an absence of synchronization. The synchronized response seen in the interacting system is underpinned by quantum effects. There is long-lived observable entanglement in the system, provided the frequencies of the spins are not too disparate.
Our work provides an understanding of how synchronization can occur in a broad range of quantum systems, as opposed to in a single, delicately controlled setup. Understanding the harmonized responses of quantum cooperative systems plays a critical role in forming quantum metrological instruments which can outperform their classical counterparts.